So in this lecture, chapter 2, we're going to be talking about biological modeling, chance, and entropy. So this is essentially an introduction to modeling and how we can go about characterizing and quantifying certain scenarios. So the first thing I want to do is go through a few key things from the previous lecture. It'll just be super quick. Then go through a main lecture. We're going to go through the genomic size of viral DNA, just as an example of what can be calculated using an approximation. Then we're going to look at coin tossing and entropy to look at chance and probabilities. And at the end, we're going to take a look at the elasticity of a chain model. So we're just going to go through a few different examples, and at the very end, we're going to be able to use our knowledge to calculate the genomic size of viral DNA. So first, a quick recap. There are a few important topics that we talked about in the previous lecture. Number one is that there are 4 main macromolecules. It would be good for you to know their names and be able to know their function as well. You should probably know the difference between unity and diversity and the different ways of viewing life, which I'll explain a little bit more in this time because I didn't do so in the previous lecture. So the 4 great macromolecules, you have nucleic acid, lipids, proteins, and carbohydrates. Once again, we won't really be focusing on carbohydrates, but nucleic acids play a role in storing and transmitting genetic information. Lipids are going to store long-term energy, and they can protect through the formation of barriers and lipid membranes. You also have proteins. They do most of the work inside cells, so they're going to incur a lot of function and regulation of the host. So when we talked about life last time, life was basically looking at the different components that make up living systems. So when we look at life at the molecular level, we just know that all living things are made of cells. When we look at the different types of cells, we know that there's going to be some diversity. However, if we zoom in far enough, everything's just made up of carbon, oxygen, nitrogen, so on and so forth, the same few sets of atoms. So that infers some sort of unity across all types of diverse components. So last lecture, we defined life as the embodiment of components that make biological systems work. So throughout this course, we're going to look at different aspects of life. So we know that this life, or basically the biological components, can assemble themselves into chains, so like polymers. We know that it organizes itself with information, so there's protein sequences, DNA, etc. We know that life can occur in and interact with water. So this is what I was talking about with the solutions. A lot of what we're going to be studying occurs within solutions. So we have to consider their interaction within a hydrophobic or hydrophilic environment as well. Life obviously contains energy. So no matter whether you're looking at higher levels or lower levels, you're still going to have to look at the energetics of everything that's happening in a process. And last but not least, this one has been passed on from different professors in this course, but life is chancy and random. So basically, this refers to the fact that sometimes, like for example, Brownian motion or the random walk model, there are different parts that are going to be affected just simply almost like the toss of a coin. So in this lecture, we'll be talking about biological modeling and how we go about doing it with examples. So the first thing we should do is go through the steps to creating a biological model. After that, we're going to start from the building blocks and see how we can create different types of models. So let's first start off with what modeling is. So a biophysical model is a simulation of a biological system that is based upon the physical properties of that system. So that means having an assumption, or many assumptions will have to be made. It also means that certain features are going to have to be ignored. A model is never going to be the perfect model. You can never parameterize every single thing that affects a living organism, or else that model would just become way too complex. So we have to make some sacrifices when we build models, and we'll find throughout this course that even if we do make those sacrifices, our models, the more parameters we add in, we just need to find a good balance. But it doesn't mean we have to ignore everything all the time. Maybe if you're studying electrophysiology, you want to include more electrically related parameters into your model, like ion charge, etc. Whereas if you were studying the physical effects of something, you would want to study a more mechanical model, like maybe a model based on springs, elasticity, so on and so forth. So essentially what I'm trying to say is that we get to choose what we want to study from whatever system we're looking at. If there are tons of variables and parameters, it's our job to figure out which ones are important and which ones are not as important. So I'm just going to quickly go through verbally an example, which is DNA. If we care about its chemical nature, we have to use a model that has sequences and binding sites. That to me would be fairly obvious because in order to figure out the interactions that our model would produce and have that match the interactions that its real chemical structure would produce, we would have to take a look at what it's made up of, so its sequence as well as binding sites, to see those interactions. But if we wanted to look at DNA's behavior, we then choose between different types of behaviors. It could be behaviors due to a charge, it could be behaviors due to elasticity, or even thermal undulations. So we can model DNA, number one, through different perspectives, and not only that, but we can model DNA or DNA's interaction in different mediums. So there are so many different ways to model something. It's up to us to try and figure out how best to do so. So my suggestion is to always start with the easiest, simplest model. Even if you think it's too easy, start with what you know first and work your way up until the model fails, or if you're having difficulties trying to get it to work well. Obviously, you don't want your first model to fail, but introduce more and more elements until it's basically too much to handle. So as Albert Einstein said, he said, make things as simple as possible, but not simpler. So what that means is we're trying to find a perfect balance for every biophysical model we make. And usually that perfect balance has to do with time and funding. So let's say you have a program that you need to write, a program script you have to write to model some sort of biological function. If you add maybe 5 parameters, maybe that program will run for a few hours. If you add a few more parameters, maybe it runs for a few days. So depending on how much time you want to spend on not rendering, but being able to process that information, it's going to make or break whether you stick with that model or not. So, for example, if I use a model and it takes 1 hour to run one trial with that model, then I probably can do multiple trials and keep running that experiment over and over again, or keep generating more data. But if I have a model that takes days or maybe even weeks to run, then it's probably not very convenient. It's very taxing on my time and probably funding from other sources. So over here we have the genomic size. We're trying to figure out the genomic size of viral DNA. If you take a look at this picture and you look closely, it's probably better if you look at it through your notes. But this is a bacteriophage, and It's an electron microscopy image of the bacteriophage's genome that has escaped its capsid. So it's a ruptured bacterial virus with DNA spilling out. So you can actually see like this spaghetti-like structure that's all over the image, just because it's DNA that has spilled out. So it's pretty cool. And what we can do is actually try and find the physical size of this genome. So physical size means the amount of physical space occupied by DNA. So there's this one strand over here. I can essentially just take a look at that strand and see how much physical space is being occupied by that piece of DNA. However, that doesn't really tell me much about genomic size. The genomic size is the length in base pairs of the DNA. So please keep in mind there's a difference between physical size and genomic size. And through this, the question is whether we can estimate the genomic size of DNA by examining the physical size of randomly spread DNA. And the answer is yes. You can also analyze the physical size of DNA if you know the genomic size. So what do we need? We need a model that relates the physical size of DNA, which we call R, to the number of base pairs. So we call that NBP. We need to have some known values, and we're going to work towards that at the very end. So at the end, there is going to be a calculation, but it's going to be more so calculating the physical size of DNA by examining the genomic size of what it is. Oops. So with all this talk about modeling, how do we know what's right from wrong? So if you're simplifying something, the greatest fear is probably that you're simplifying it way too much. And usually an oversimplification means that your approximation is going to be pretty bad. So this is really rooted in foundational or fundamental knowledge. If you already know something, then that's good. If you have proven averages or measurements that have been taken in the past, then you should probably use them. So examples would be the length of the DNA base pairs, so that's usually known through other studies, the length of a mitochondrion, the diameter of a nucleus in organelles, and the thickness of lipid bilayers, such as 5 nanometers. So you can use all of that information in your model as known values. And if you stick with that, you can introduce more and more variables and make your model more accurate. So start from your foundational knowledge and work your way up towards more random variables that you'll have to monitor carefully. So then to answer the question, what defines a wrong model? There are several ways that you can arrive at that. Number one, there's absolutely no relevance to the system. So for example, if I'm studying lipid membranes and suddenly I introduce a parameter that only affects proteins. So that would probably not be good because it has nothing to do with lipids at all. So make sure you have the correct parameters when you're making your model. Number two, maybe there's a lack of detail. Maybe I'm trying to model the ion channel flux, so trying to see the surface potential on one side of an ion channel, and I've completely forgotten to include any sort of measurement for electrical activity. So that would be a lack of detail, having a model that's just way too simple and only based on the electrochemical gradient, for example. Next, you can make too many assumptions. So if you have, let's say, 10 different parameters that affect a model, and you have 8 that you just made assumptions on, then you're probably 80% wrong already, because you can't just make assumptions. You can try and simplify something. For example, if you have that one parameter that you really aren't sure about, then maybe change it regularly. So let's say you have variable A that you have to change. If you don't know what it is, then you have to assume maybe that variable A is equal to 1. Run some experiments or run some trials with your model, see if it works. If it doesn't, try A equals 2, A equals 3, so on and so forth. So try to limit your assumptions, and even when you do make assumptions, go through a few possibilities so that you can see which one is the most applicable. Last, we have the perfect model. So this is kind of a conundrum because the perfect model should give you the perfect results. But actually, if you have the perfect model, which means you've basically done everything correctly from beginning to end, but you arrive at completely incorrect results, then that means that something is fishy about this. It means that if you have a model that has all the right parameters and all the right estimates, and it makes sense, but you obtain results that go against all known predictions, it's usually a perfect chance to learn something new about what you're studying. And it's these types of models, these perfect ones that go wrong, that lead to breakthrough experiments, because you're trying to figure out why on earth your model has produced these results. So learn from each experience, and basically every single model you create will become better than the previous one. Now, we talked about life being chancy and random, and it's time to talk about different elements of that. So we're going to go through coin tossing, chance, and entropy. For example, what are the chances we all get to stay home all day and play video games? Probably not. We still have to work. So we're going to first talk about randomness to multiplicity, then multiplicity to entropy, and then look at entropic elasticity and random walk models. So because of the possibilities in life, this introduces probability. So we're going to use coin tosses as a simple model. Looking at our future models, we do have to talk about probability, because when we introduce a model, we have to say this is the most probable outcome, because there can be so many outcomes for configurations of molecules and so on and so forth. Our goal is to try and find the most probable one. So going forward with coin tosses, if we look at 2 coins, that means we can either get heads or tails. And let's say we toss it n times. Then we get different possibilities of sequences. We can have all H's, like this one. We can have all T's, like this one. Or we can have a combination of H's and T's, like we see here, and many other options. So we know that all sequences are equally probable. So the chances of getting this sequence and this sequence and this sequence, they're all probable. But if we take a look at just the sequences themselves, it makes everything unpredictable. They all have an equal chance of having the same outcome, so that's not good for any model, and that's not good for us. So instead of taking a look at the order of values for sequences, we look at its composition only, and that leads to something called multiplicity. So if we don't look at the order, then the composition or number of H's and T's becomes a lot more predictable, which means that the most probable composition or state can be predictable as well. So looking here, I can see that there's only one chance for me to get all H's, and there's only one chance for me to get all T's. But there's at least 2 chances for me to get 2 T's, and however many H's are left over. So I can have a T here and a T here, a T and T. So the 2 T's in a sequence can be rearranged in many different ways, which means just comparing it to a scenario that has all T's, it already has a higher chance of happening. So the number of sequences that have the same composition is called the multiplicity of that sequence. And we'll cover that in the next few slides. So now let's take a look at the randomness of coin flips. So let's assume that all of these coins here are being lowered into boiling water and that they're at the tips of long needles. Basically, there's nothing else affecting it except the boiling water. So the movement of water, because it's bubbling randomly, it can flip the coins from heads to tail or vice versa. And the question we want to ask is, what is the system going to tend towards? So we know that the most probable composition is 50-50 heads and tails. A closed system is going to tend towards a higher state of multiplicity. So that means if the most probable composition is 50-50 heads and tails, it means it has a higher multiplicity, and that means a higher disorder. And that disorder means that there is a greater number of each option. So just to recap, if you have greater disorder, that means there's going to be more ways that you can rearrange things. And it's good to remember that at high multiplicities, there's going to be higher disorder. And what does this tell us? It tells us that closed systems are going to lean towards a state of higher disorder. So when you put all these coins into boiling water, the assumption is that it'll have a higher chance of half of them being heads and half of them being tails. But the question is, how can we quantify this? We can now define multiplicity, W, as the number of sequences with the same composition. So looking back at our coin toss model, we chose n, little n, to be the number of H's, and let's choose capital N to be the number of tosses. Then the difference would be the number of tails. And we're going to define multiplicity as follows. We have W as a function of n and n, and it's equal to capital N for the number of tosses divided by little n factorial time. So basically the number of heads factorial times the number of tails factorial. So although each toss is random, the composition is predictable with great precision. And looking at the probability graph here, let's take a look. We have n being this, so basically the number of heads, and this would be our multiplicity. So we see that at the number of tosses divided by 2 point, this is the most probable, giving us an equal split of heads and tails. So every toss is going to be random, but if we just take a look at composition and multiplicity, then everything becomes predictable with fairly great precision. Now, we talked about multiplicity and disorder. It's now time to find a connection between the two, since we're going to use this for the rest of the term. So Ludwig Boltzmann was the one who did this for us. He was able to make that connection. He was able to connect the microscopic world, so that would be through multiplicity, looking at the composition of sequences, to the macroscopic world, so that would be entropy and energy. He said that entropy was proportional to multiplicity through a logarithm, and that entropy S is equal to some constant times the natural logarithm of multiplicity. So this constant, 1.38 times 10 to the negative 3 joules per Kelvin, became what's called the Boltzmann constant, which you've probably heard of before in thermodynamics and chemistry as well. And in fact, he was so famous for this equation that he had that equation engraved on his tombstone along with a bust. So that's pretty interesting. I probably would have put my name on there, but to each their own. So now, from our previous few slides, we understand that any system will tend towards a higher state of entropy. So we're always tending towards disorder. And in fact, because all systems tend towards entropy, we can consider entropy like an arrow of time. So what this means is, as time progresses, the assumption is that there's going to be more and more entropy, which means that if you take a snapshot along a timeline, a snapshot at point A and a snapshot at point B later on in time, at point A, you're probably going to have lower entropy, and at point B, you're probably going to have higher entropy. So a specific example would be looking at particles in a box. The system over time is going to tend towards a higher entropy S, so the particles are going to distribute more and expand the box. So just looking at the box itself and the particles, over time, they're just going to, if they're all the same molecules, they're going to try and rearrange themselves randomly, and the assumption is that they're going to tend towards that higher state of disorder. So putting everything together, here's the equation for entropy. So S equals KB ln of W. And we know that multiplicity is defined as this. So we just plug that in and we now have an updated equation for entropy. This equation would be good to know because we'll be using it probably throughout the term to see which system or which of our models and which of our predictions are going to be the most probable. So with our overview into entropy covered, let's take a look at modeling the elasticity of polymers. So since we can assume that these are entropic springs, so basically if you have a polymer, it wiggles around, and we can assume it kind of looks like a spring, just like my example before in the previous lecture of comparing everything to springs, just so we can get different graphs to compare it to. So since we can assume these are entropic springs, it means that A, there are many configurations of the polymer, and B, we have to figure out which configurations are higher in entropy and therefore higher in multiplicity and probability. So if we just take a look at a sample coil of DNA, for example, or any coil molecule, there's a distance x on the left that it can be stretched, and it can also be anchored at one end to kind of look like a spring. So this distance x is basically the physical size or the length that DNA takes up within the space. So now let's take a look at two examples and compare their entropies just visually. I have a fully stretched option. In order to fully stretch something and in order for some polymer to be perfectly rigid, that means it has to be very ordered instead of disordered. So that means it's going to have less entropy, with L being the total length. Then you have the partially stretched model. So now you have some coil, lots of coil, some sort of coil system, and you have a distance x. So it's not L, but rather x for the physical size or physical distance that the entire strand takes up. And as you can see visually, it's a lot more disordered, and there's going to be more entropy. So in real life, if you stretch a string so that it's taut, when you let go, it's probably going to get a little bendy, and so it's going to go towards its natural state, which already is a little bit disordered. So just by looking at these two models visually, we can make the assumption, or very simple assumption, that these states are more likely than that state to occur naturally. And hopefully you agree with me, because if you get a string and just throw it on your table, it won't automatically love to go into a straight line. So polymer configurations, we can also use entropy when we look at polymer configurations, so how each building block gets connected to one another. Any chain molecule can be depicted as beads on a string. So once again, you can have lots of configurations like this, and our job is to figure out which one is more predictable. So this slide basically builds up upon the previous slide, but now we're looking at a polymer chain, and we define the starting point to be your first building block. So you label them 1, 2, 3, 4 all the way to the very end, and let's say this is N. So from 1 to N, that distance is called R, and that basically refers to the physical distance of a polymer. So with our previous knowledge, we know that as entropy increases, the amount of folding and coiling with DNA made the tail to head distance much shorter. So that would be the X that you saw previously. So if I just compare these three models here, the R here from 1 to N is given. The R from one end to the other here seems to be longer, and it is because there's less kinks or coils in this polymer chain. This means it's probably going to be less disordered or more ordered, so it would be a system of lower entropy and therefore lower probability. This distance, let's just assume this distance is the same as the one over here. That means that there's an equal chance that your polymer sequence is going to end up having these two configurations. So in the next few chapters, we'll be going through examples where we try and figure out whether there's only one most likely configuration or whether there's 2 or 3 probable but equally probable configurations for polymers. So another way to mimic a polymer would be to use a simple random walk model. And what a random walk model is we place our building block on one corner of a rectangular lattice. So this would be our lattice in black. And we have a purple point here to represent our building block. So then this can jump from that starting point to neighboring sites. So it can either go this way or this way, but there's an equal chance, 50-50 split, that it goes either way. So through a program, you'll be able to come up with various different configurations for using the random walk model, and then you can calculate the distance R from tail to head and be able to compare the physical distance for each of those possible outputs. So remember, the smaller the R, the more likely the configuration, at least with the simplified model that we've presented. So now, if we're trying to go back to our first few slides and we're trying to model the genomic or physical size of viral DNA, we need to be able to estimate the size of some polymer in solution. So remember, when the viral DNA spilled out of the capsid, it was really wiggly and swirly. That means we can break it up into polymer chains and calculate R, which would be the distance from tail to head, or tail to tip. So if we're trying to model the size of a polymer in a solution, we need some parameters, and we'll go into this equation in a lot more detail later on in the course. But for now, I just want to present it to you. So the 4 main parameters we have to look at would be the end-to-end distance. So that would be called R. That's the distance from tip to tip of the polymer chain, and is actually given by this equation, which we'll prove later on. We have the square root of R being approximately equal to 2 times L psi p. So we'll explain these two. L is the contour length, so basically how much bending there is with your polymer, and your persistence length, psi p, is the maximum length where the polymer is considered rigid. So what that means is, because we're looking at the molecular scale, there's something called a persistence length, where if you're zooming in far enough, so let's say you have 20 nanometers, At 20 meters, there's going to be some sort of bend. Or 20 nanometers, there's going to be some sort of bend. But maybe if you look at 19 nanometers, it looks like a rigid rod. So there's going to be some length in that polymer chain where you can consider each individual chunk of polymer to be rigid. So those would be those models that you see where you have those sticks that are connected to each other. Every stick is of a persistence length. So more on that later, but we now have contour length, persistence length, we have R, and we get this equation. But the value of R probably isn't the greatest estimate of distance. We want to be able to calculate the average distance between monomers, well, at least integrate the average distance between monomers as well as the center of mass of the polymer into our equation. And this is where this term came from, the radius of gyration. So Rg is usually the best and most precise measure of polymer size because it takes into account the polymer center of mass, which takes into account its individual building blocks, and it also takes into account the distance between those building blocks. So this gives us a much more accurate model, which we'll derive later on as well, but we have the square root of the radius of gyration squared so that you can actually get Rg, and it's approximately equal to the square root of the persistence length times contour length divided by 3. So we'll be using this for our next practice problem. So now let's answer the question we asked earlier in this lecture. We want to measure the genomic and physical size of viral DNA from the electron image here. So if we want to estimate the size of viral DNA, what parameters are we given first? So we know that DNA is made up of base pairs, and we know that the length of one base pair, which is the contour length, is approximately, sorry, not the contour length, it's just the length of a base pair, LBP. It's 0.34 nanometers. And the persistence length is something we haven't covered yet, but we can say it's about 50 nanometers for now for viral DNA. The genome length is about 150 kilobases. So we'd have to multiply by 1,000 to get the number of base pairs. We also have this equation that we presented before. And keep in mind that whether we're looking at physical size of viral DNA or genomic size of viral DNA, doesn't matter. This technique will allow you to calculate both depending on what you start out with. So if you're just looking at this image and you know that there are 150 kilobase pairs, then you can calculate the physical size. If you wanted to look at this picture and measure a whole bunch of different R values, then you'll be able to figure out the number of base pairs as well. So for us, it would be super tedious to start measuring all this. It just looks like spaghetti. So we're going to do the opposite. We're going to start off with the known number of base pairs and then calculate the physical size of this. Okay, so let's go through things step by step. We have the physical size of viral DNA being approximately equal to the square root of L times psi p, which is the persistence length, divided by 3. So L is the contour length. So that's actually the total length of the chain. So if we want the total length of the chain, it would basically be the length of our base pair times the number of base pairs we have. So we have LBP times NBP, and the persistence length doesn't change. So then we plug in our values. We have the square root of 0.34 times 150 times 1,000 times 50 divided by 3, and we square root that to get approximately 921 nanometers or 0.9 micrometers. So this is the average size of DNA seen from the figure, it's actually comparable to the real answer, but a bit larger, just because of the length scale of the exploded DNA. So to end off, it's not the greatest model just because there aren't too many parameters involved and there are so many configurations possible, but it's a good starting point for us to discuss modeling. So what did we learn today? We went through an introduction to modeling. So we can model complex biological systems by looking at one feature at a time. And number two, which is the most important, if you have a closed system, it's going to tend towards higher entropy, and multiplicity usually occurs in the middle of two extremes. So that means the most probable multiplicity is going to occur in the middle, so with that curve that we saw. The higher the multiplicity, the higher the probability that it will be a result. And last, it takes force to reduce entropy. So if we wanted a polymer chain to be completely rigid and straight, we would have to introduce some sort of force in order to make it more ordered. So hopefully this gives you a good introduction to modeling and what we're trying to achieve in this course. But do remember the equation for entropy, because we'll be using it quite a bit later on.